Okay, so we're still working on 3E, and we found that the concentration was so small, or that the KB is so big that you kind of have to do the quadratic. It's iffy. It's in a range where some people would do it to be diligent and others wouldn't. I'm not going to show you that math. If you're still struggling, if you are struggling with that quadratic and how to do it and when to do it, then come talk to me and we can work on that together. But what you end up with is a formula 5.41 times 10 to the negative 6 minus 0.000178 minus x squared equals 0. So my A term is -1. My B term is, let's see, where'd it go? There's my x. So this is the B term, and your C term is this. And so solving for the quadratic gives us two values, but I'm going to ignore the one that's negative because, of course, I know concentrations can't be. And so we're going to go with 2238 molar. And I remind myself that X value is hydroxide. Okay. So then I would go the negative log of X equals POH. And what I get for that is 2.65. Right? And so 14 minus 2.65 will give us the pH at the equivalence point, which is 11.35. Okay. So the last question is past the equivalence point where we've added 40 milliliters now. I want to figure out the number of moles of base that is equivalent to. So I have to subtract out all the base that reacted to figure out what volume is left. Oh, so I should probably label this. This is 3E. Okay, and then I take that and I figure out how many moles that is equal to. Again, using stoichiometry. Oop, I forgot to convert my liters, so I can do that over here. That's okay. So milliliters cancels, liters cancels. And we end up with moles of OH minus that are left over, which is 0.0008447. And that's moles OH minus. So at this point, we've kind of broken, our pH is way above what it was at the equivalence point, and so the pH is due exclusively to the amount of hydroxide that we have hanging out. So if I can figure out what the concentration of the hydroxide is, then I can just plug that into pOH. So it's the negative log of that number, that many moles, divided by the total volume at the end, at this point. So it's going to be 25 milliliters plus the 40 milliliters. I want that in liters, though, so I convert. And what we find is that it becomes the negative log of 0.012995, and so that equals 1.89. And then our final step here is to just take 14 minus 1.89, and we get the pH at the end, which is 12.11. So we can actually go back to the original graph and see if these numbers make sense. Okay, so at point E, we have 12.11. So, sorry, that was F. E was the midpoint. I labeled that wrong. Let's fix that. This is F. Okay, so 12.11 right here is the pH. So you could even sort of draw it on the axis where it belongs if you wanted to. The equivalence point pH was, let's see, we got 11.35 for E. Okay, and So that means this point is 11.35. Midpoint 1 was D. We got 10.25 there and 9.5 for C. My iPad does not like to let me write on the edge of the page. And then C was 9.5, and C was our equivalence point, so that's going to be about here. B, we got 5.6, and for A, we got 3.76. So I think everything kind of makes sense based on what we expected. Certainly, let me say 3.76. Certainly, the pattern holds. We're increasing in pH as we go along, and it's pretty predictable and pretty consistent, so that's good news. Okay, so the final questions is to label everything, which we kind of already did in this graph. And question number 5 is really a critical idea because it saves you a lot of work, particularly on your lab report. And the idea there is that when you're at the midpoint, so in our case, here's midpoint 1, pKa and pH are the same thing. So if midpoint 1 is 5.76, then that means that's my pH and my pKa. Midpoint 2 has a different Ka, it's higher, it's 10.25 for the pKa, but that's how you get it.